Computer Science 475, Computer Architecture, Instruction Sets, Characteristics and Functions. This corresponds to Chapter 12 of the 10th edition of the Stallings textbook. So, begin with an introduction and talk about a lot of the hardware stuff that we've discussed so far. It's not necessarily apparent to a programmer in a higher level language what this means, but the machine instruction sets that we'll be discussing certainly are apparent to the programmer and play a major role in everything that's written in assembly or even higher level languages in terms of how efficient certain instructions are. And descriptions of the instruction sets also explain a lot about the processor or processors and the capabilities of the machine. So let's delve right into it with machine instruction characteristics and talk about those for a little bit. So the operation of the processor is determined by the instructions it executes, and this is referred to as the machine instructions or computer instructions. The instruction set is the collection of different instructions that the processor can execute. Each instruction must contain the information required by the processor for execution. And this goes back to something we saw in Chapter 3, the instruction cycle. And hopefully this is something you recall from Chapter 3. It's actually figure 3.6 on page 88 of the 10th edition of the textbook, but it reappears in figure 12.1 on page 414. Hence, it's pretty important in the overall scheme of the text and the topic that we're discussing. So the main idea is to calculate the address, fetch the instruction, decode the instruction and calculate the operand address for this, fetch the operands, perform the specified operation, and then store the results, or put more simply, fetch, decode, and execute. By implication, the diagram defines the elements of a machine instructions. These elements are the operation code that specifies the operation to be performed. For example, add or I/O. The operation is specified by a binary code known as an operation code or an opcode, and a lot of times we use mnemonics for those, which it'll become apparent because a lot of us don't speak binary as a native language. The source operand reference. The operation may involve one or more source operands. That is, these are the inputs for the operation. For example, if you're adding two numbers, you'll need those two numbers as the operands for that operation. The result operand reference. The operation may produce a result. For example, if we were adding those two numbers, we would need to know where to store the result. And then the next instruction reference, which will tell the processor where to fetch the next instruction after the execution of this operation is complete. So where do we find these operands? Well, there are four places where you can find them. In main or virtual memory. As with the next instruction references, the main or virtual memory address needs to be supplied. Basically, where do I find them in main memory? I need their address. They may be found in an I/O device if we're receiving input from a keyboard or from a mouse. The instruction must specify the I/O module and the device for the operation. If memory mapped I/O is used, this is just another main or virtual memory address. They could be found in the processor register or registers, and processors contain one or more registers which may be referenced by the machine instruction. If more than one register exists, then each register is assigned a unique name or number, and the instruction must contain the number of the desired register. Or they could be immediate, in which case the value of the operand is contained in a field and the instruction being executed. And you can typically find both the source and result operands in those four different areas. That is, where do we get the information and what do we do after we make that calculation. So instructions in the machine are represented by a sequence of bits. The instruction is divided into fields corresponding to the constituent elements of the instructions. So a simple example is in the figure below. We have 4 bits that correspond to the opcode, 6 bits that are the operand reference, and 6 bits that are the second operand reference. Binary is a pain, so we often use symbolic representation. For example, add, mul for multiply, load, store, div for division, and sub for subtraction. With most instruction sets, more than one format is used. During instruction execution, instruction is read into an instruction register in the processor. The processor must be able to extract the data from various instruction fields to perform the operation. It's difficult for the programmer and the reader of textbooks to deal with the binary representations as we discussed a slide back. Thus it's become common practice to have symbolic representation or mnemonics of the machine instructions. You might recall some of those from the IAS discussion in Chapter 1. But it's probably really pushing it because that was quite a long time back. So we can also represent operands symbolically. For example, add RY may mean add the value contained in data location Y to the contents of register R. In this example, Y refers to the address of a location in memory, and R refers to a particular register. Note that the operation is performed on the contents of the location, not its address, and that's a distinction you probably remember from CS410 when we talked about pointers, that addresses are different than the values stored at those addresses. So it's possible to write a machine language program in symbolic form, and each symbolic opcode has a fixed binary representation. The programmer specifies the location for each symbolic operand. For example, the programmer might begin with listed definitions. Say set x is equal to 513 and y is equal to 514, and so on. A simple program would accept this symbolic input, convert opcodes and operand references to binary form, and construct the binary machine instructions. In fact, this is what the assembler does. Machine language programmers are pretty rare nowadays to the point of non-existence. Most programs written today are in high-level language, or failing that, assembly language, which we'll discuss a little bit later on in the book. However, symbolic machine language remains a useful tool for describing machine instructions, and we're going to use it for that purpose. So let's take a look at some of the instruction types. The first up is data processing. These are arithmetic instructions that provide computational capabilities for processing numeric data. Logic operations operate on the bits of a word as opposed to rather than the numbers. Thus they provide capabilities for processing any other type of data that a user may wish to employ. Data storage is another category. Movements of data into and out of the register or memory locations. And really a computer should have a set of instructions that allow the user to formulate any data processing task. And another way to view this is to consider the capabilities of high-level programming language. Any program written in a high-level language needs to be translated into the machine language to be executed. Moving on with our instruction types, another type is data movement, and here I/O instructions are needed to transfer programs and data into memory and the results of the computations back out to the user. And last but not least, control instructions. These are test instructions that test the value of data word or the status of a computation, and branch instructions that are used to branch to different sets of instructions depending on the decision made. These are your control structures. So one of the traditional ways of describing processor architecture, and this has been a long time, is the number of addresses contained in each instruction. And it's become somewhat less important in terms of describing architecture, but it's still useful in understanding the operations of the processor. So what's the maximum number of addresses that you need? Well, arithmetic operations take the most input. It's going beyond storing a single value or branching to a particular instruction. So typically, if it's a binary operation, we have two operands along with their addresses. One address in which we're going to store the result, and one address for the next operation. That gives us a total of 4 addresses. Of course, you can use fewer, and we'll see some examples of that. So here's where we might have fewer addresses. This figure compares typical 1, 2, and 3 address instruction formats that could be used to compute the equation y is equal to a minus b divided by c plus d times e. With 3 addresses, each instruction specifies 2 source operand locations and a destination operand location. Because we choose not to alter the value of any of the variables that we have, we use a temporary location known as t to store some of the intermediate results. And there are 4 instructions, and the original expression had 5 operands. The 3-address instruction formats are not common because they require relatively long instruction format to hold the 3-address references. With 2-address instructions, that's the second one on the left, instructions of binary operations, one address must do double duty as both an operand and as a result. Thus, the instruction sub yb that's pointed to carries out the calculation y minus b and stores the result in y. The 2-address format reduces the space requirement, but also introduces some awkwardness. To avoid altering the value of an operand, a move instruction is used to move one of the values to a result or temporary location before performing the operation. Our sample program expands to 6 instructions from the 4. Simpler yet is the 1-address instruction. For this to work, a second address must be implicit. This was common in early machines, with implied address being a processor register known as the accumulator. Now, the accumulator contains one of the operands and is used to store the result. In this example, there are 8 instructions that are needed to accomplish the task. It's possible to make do with 0-address for some instructions. 0-address instructions are applicable to special memory organization called a stack. A stack is, as you recall from 151, it's a last in, first out set of locations. The stack is a known location, and often at least the top 2 elements in the stack are processor registers. Thus, 0-address instructions would reference the top 2 stack elements. If you want more information on how stacks are used, you can look at Appendix E. And we also discuss them a little bit more in this chapter. So the number of addresses per instruction is a basic design decision. Fewer addresses per instruction results in instructions that are more primitive, requiring a less complex processor. It also results in instructions that are of shorter length and require more instructions to accomplish a task. On the other hand, programs contain more total instructions, which in general results in longer execution times and longer, more complex programs. So, for example, with the 1-address instruction, you see it's a longer, more complex program. With 1-address instructions, the programmer generally has available only one general purpose register, the accumulator. With multiple address instructions, it's common to have multiple general purpose registers. This allows some operations to be performed solely on the registers. Because register references are faster than memory references, as you'll remember from the memory hierarchy, this speeds up our execution. And again, that goes back to the designing for performance that was the subtitle of the text. For reasons of flexibility and the ability to use multiple registers, most contemporary machines employ a mixture of 2 and 3 address instructions. The design trade-offs in choosing the number of addresses per instruction are complicated by other factors. There is the issue of whether an address references a memory location or register. Because there are fewer registers, fewer bits are needed to indicate a register reference versus a memory location. And as we'll see in the next chapter, a machine may offer a variety of addressing modes, and the specification of mode taking 1 or more bits. The result is that most processor designs involve a variety of different instruction formats. So, instruction set design. This is the programmer's means of controlling the processor and affects many aspects of the computer. There's a lot of disagreement as to the optimal design, and these issues are highly interrelated and have to be considered together in designing an instruction set. The book, of course, must consider them in sequence, but they do make an attempt to show the interrelationships. And so some of these fundamental issues are the operation repertoire, how many and which operations provide, and how complex they should be. The data types, the various types of data upon which the operations are performed. Instruction format, the instruction length in bits, number of addresses, size of various fields, and so on. Number of processor registers that can be referenced by instructions, and how do you use them. And addressing the mode or modes by which the address of an operand is specified. And again, we brought that up with registers requiring fewer bits to address than memory locations. This brings us to different types of operands. And this is section 12.2 of the text. This is a nice figure from the author, so I thought I would include it here. Anyway, the machine instructions operate on data. The most important general categories of data are addresses, numbers, characters, and logical data. We'll see in chapter 13, the next chapter, that addresses are in fact a form of data. Now you probably know that from studying pointers in C++. In many cases, some calculations must be performed on the operand references if an instruction to determine the main or virtual memory addresses. In this context, addresses can be considered unsigned integers. Anyway, the other three get their own slides, but memory just gets this footnote. Basically, consider memory addresses as a type of operand, and you'll be familiar with them from the work that we did with pointers in some of the early programming classes. The other common data types are numbers, characters, and logical data, and each of these gets briefly examined. Beyond that, some machines define specialized data types or data structures. For example, there may be machine operations that operate directly on a list or a string of characters, and that probably gets more into Lisp, and I believe that was the IBM 701 that did that. So numbers. All machine languages include numeric data types. That shouldn't be a surprise. Numbers are stored in a computer, and they're limited by the magnitude of the numbers representable on the machine. And in the case of floating point numbers, a limit to their precision, which you might be familiar with from IEEE 754 standard. Three types of numeric data are common in computers: binary integer or binary fixed point, binary floating point, and decimal. And some machines operate on something called packed decimal, where each decimal digit is represented by a 4-bit code with 2 digits stored per byte. To form numbers, 4-bit codes are strung together, usually in multiples of 8 bits, although there are some tricks to make it more optimal. A common form of data is text or character strings. Textual data in character form cannot be easily stored or transmitted by data processing and communication systems because they're designed for binary data. However, we do have standards for representing them. The most commonly used character code is the International Reference Alphabet, or in the United States, the American Standard Code for Information Exchange, or ASCII. Another code used to store characters is Extended Binary Code Decimal Interchange Code, or EBCDIC, and this was used on IBM mainframes and probably still is. Logical data, an n-bit unit consisting of n 1-bit items of data, each having a value of 0 or 1. There's two advantages to this bit-oriented view. One, memory can be used most efficiently for storing an array of Boolean or binary data items in which each item can take only on the values 1 true or 0 false. And to manipulate bits of data in the item, if floating point operations are implemented in the software, we need to be able to shift these significant bits in some operations, and we can convert from IRA to packed decimal. Normally each word or addressable unit, byte, half word, or so on, is treated as a single unit of data. It's sometimes useful, however, to consider an n-bit unit as consisting of n 1-bit items of data, each having 0 or 1. When data are viewed this way, they're considered logical data. And there are two advantages to this. First, we may sometimes wish to store an array of Boolean or binary data items in which each can take on 0 or 1. And with the logical data, we can basically perform very efficient operations on it using the shifts and the rotations that we'll talk about later. I think my footnotes may have repeated that, but it's worth repeating. Now we'll move on to section 12.3, and these are the data types in the Intel X86 architecture and the ARM architecture. And as you can see from this figure, there are quite a few of them. The X86 can deal with data types of 8, 16, 32, 64, and 128 bits in length. To allow maximum flexibility in data structures and efficient memory utilization, these words, which are the 16-bit ones, need not be aligned at even number addresses, and so there are mechanisms for dealing with them when they're not completely aligned. Likewise, double words, which are the 32-bit ones, don't necessarily need to be aligned to addresses evenly divisible by 4, and so on. The processor basically can convert the request for misaligned values into a sequence of requests for the bus transfer. It's interesting to note that with the Intel 8086 machines, the X86 uses little Indian style. That is, the least significant bits are stored in the lowest addresses. The appendixes chapter has details on the Indians, but as a summary, big Indian byte order, the most significant byte, the big end of the data, is placed at the byte with the lowest address. The rest of the data is placed in order of the next 3 bytes in memory. Little Indian, the least significant byte, the little end of the data, is placed at the byte with the lowest address. The rest of the data is placed in order in the next 3 bytes in memory. So, as you can see, there are quite a few different data types that the X86 supports. And the one down at the bottom is known as packed sim, single instruction, multiple data, that's actually used for a lot of multimedia and came in around 1996. So, numeric data formats. Here you can see the X86 numeric data types. The signed integers are in 2's complement representation and can be 16, 32, or 64 bits long. The floating point type refers to a set of types that are used by the floating point unit and operated on by the floating point instructions. The 3 floating point representations conform to the IEEE 754 standard, and you may have seen the standard and some of its limitations in a numerical analysis course, for example, CS410. And like I talked about in the last slide, there are also the single instruction multiple data types. These were introduced in the X86 architecture as part of extensions to the instruction set to optimize performance on multimedia application. There's an example with fade in and fade out. In terms of ARM processors support data types of 18, 16, and 32-bit word length. Bit length, 32 being the word, 16 being the half word, and 8 being the byte. Normally, half-word access should be half-word aligned, and word addresses should be word aligned, so you don't have that ability to have things that are misaligned like you do in the X86 architecture. Although it does support 3 alternatives if they're not aligned. The default case, it's treated as truncated. There's also alignment checking and unaligned access. With the unaligned access, when that's enabled, the processor uses 1 or more memory accesses to generate the required transfer of adjacent bytes to the programmer. The other interesting thing with ARM is it's worth noting that there is no floating point type, so any floating point operations need to be implemented in software. ARM does support an optional floating point coprocessor that supports the single and double floating data point types that are defined in IEEE 754. So let's move on to types of operations. And this corresponds to Chapter 12.4. There are a number of different opcodes, and these vary widely from machine to machine. You can usually find opcodes in categories related to data transfer, arithmetic, logical, conversion, I/O, system control, and transfer of control. And Table 12.3 lists the common instruction types in each category. It's pretty long, and the section provides a brief survey of each of those the various types that are on this slide, together with a brief discussion of the actions taken by the processor. And again, the table's long, so it doesn't fit on a single slide, and I encourage you to spend about 2 to 3 minutes looking at page 426 of the 10th edition to get an idea as to the types of operations in each category. For example, logical operations that are supported are AND, OR, NOT, exclusive OR, test, which sets flags based on the outcome. Set control variables for protection purposes, left and right shifts, and left and right rotations. So here are the processor actions for various types of operations. For example, in arithmetic operations, these may involve a data transfer before and or after, to pull in the operands or to transfer out the result. Performing the requested function in the arithmetic logic unit, and setting condition codes and flags. For example, if we have a carry result or an overflow operation, those would set different flags. Data transfer, this is the most fundamental type of machine instruction. The instruction needs to specify the location of the source and the destination of the operands. Length of the data to be transferred also needs to be indicated, and the mode of addressing for each operand must be specified. Table 12.5 on page 428 shows examples of the IBM EAS390 data transfer control operations. Note that there are variants to indicate the amount of data transferred, 8, 16, 32, or 64 bits, and there are different instructions for register to register, register to memory, memory to register, and memory to memory transfers. In contrast, the VAX machine has a move instruction with variants for different amount of data to be moved, but it specifies whether an operand is a register or a memory as part of the command. So you need to specify whether you want a register or memory and where that's located. It's somewhat easier for the programmer because you have a lot fewer mnemonics to deal with. However, it's somewhat less compact than the IBM EAS390 approach because the location of each operand must be specified separately in the instruction. In terms of processor action, data transfer operations are perhaps the simplest type. If both the source and destination are registers, then it simply causes data to be transferred from one register to another, and that keeps it internal within the processor. If one or more of these are in memory, then the processor must perform some of the following actions. Calculate the memory address. If the address refers to virtual memory, translate from virtual to real memory address. Determine whether the addressed item is in cache, and if not, issue a command to the memory module to do that data transfer. Arithmetic. Most machines provide the basic arithmetic operations of add, subtract, multiply, and divide. They're provided for signed integers and fixed point numbers. Often they are provided for floating point and packed decimal numbers as well. Other operations include a variety of single operand instructions. Absolute, take the absolute value of the operand. Negate the operand. Increment, add 1. And decrement, subtract 1. Increment, interestingly, in C++ is ++, which is where C++ gets its name. So the execution of an arithmetic instruction may involve data transfer operations to position operands for input to the arithmetic logic unit and to deliver the output of the arithmetic logic unit. If you wanted to take a look at that, it's, I think, figure 12.5 that shows the movement involved in the data transfer and arithmetic logic unit operations. Most machines also provide a variety of operations for manipulating individual bits of a word or other addressable units. These are often referred to as bit twiddling, and they're based upon Boolean operations. Now, you'll no doubt be familiar with these based on your exploration of lower division courses in our curriculum, in particular discrete math. Some of the basic logical operations that can be performed on Boolean or binary data are shown in the table 12.6. The NOT operation obviously inverts a bit, and or and the exclusive or are the most common logical functions with two operands, and equal is useful as a binary test. A really cool trick to get ones complement is to exclusive or a word with another one set to all ones, and that will give you ones complement. Pictured here are the shift and rotate operations that are supported by both machines. By most machines, sorry, not both. With a logical shift, the bits of a word are shifted left or right. On one end, the bit shift shifted out is lost. On the other end, a 0 is shifted in. Logical shifts are useful primarily for isolating fields within a word. The zeros that are shifted into the word display unwanted information that is shifted off to the other end. The arithmetic shift operation treats the data as an unsigned integer and does not shift the sign bit. On a right arithmetic shift, the sign bit is replicated into the bit position in its right. On left, logical left shift is performed on all bits but the sign bit, which is retained. These operations can speed up certain arithmetic operations. With numbers in 2's complement notation, a right arithmetic shift corresponds to division by 2, with truncation for odd numbers. Both an arithmetic left shift and a logical left shift correspond to a multiplication by 2 when there is no overflow. If overflow occurs, arithmetic and logical left shift operations produce different results, but arithmetic left shift operation retains the sign of the number. Because of the potential of overflow, many processors do not include this instruction, including the PowerPC and Itanium. Others, such as the IBM EAS 390, do offer the instruction. Curiously, the X86 architecture includes an arithmetic left shift, but defines it to be identical to the logical left shift. Rotate or cyclic shift operations preserve all of the bits being operated on. One use of a rotate is to bring each bit successfully into the leftmost bit, where it can be identified by testing the sign of the data and treated as a number. As with the arithmetic operations, logical operations involve the arithmetic logic unit and may involve data transfer operations. If you want to see these, take a look at table 12.7 and gives an example, which is pictured here, gives an example of all the shift and rotate operations that are discussed in this subsection. Conversion, instructions that change the format or operate on the format of the data, for example, converting decimal to binary, which we saw in Chapter 9, or converting EBCDIC to ASCII, or vice versa. I/O operations, a variety of approaches can be taken. Basically, we discussed these in the memory management module, or in the I/O module. Isolated programmed I/O, memory mapped, direct memory access, and use of an I/O processor. Many implementations of the instruction set provide only a few I/O instructions, with specific actions specified by parameters, codes, or command words. System control instructions are those that can be executed only while the processor is in a certain privileged state or is executing a program such as the operating system that's in a special privileged area of memory. And typically these instructions are reserved for use by the operating system. Transfer of control. Sometimes you want to transfer control if you want to execute an instruction more than once. And virtually all programs involve some type of decision making, at least everything that you've done subsequent to the first program in CS410. It helps if there are mechanisms for breaking tasks up into smaller pieces that can be worked upon one at a time. And most common transfer of control instructions are branch, skip, and procedure call. And let's talk about each of those. So branch instruction, this is figure 12.7 in the text. A branch instruction, also called jump, has one of its operands the next address of the instruction to be executed. Most often the instruction is a conditional branch instruction, that is, the branch is made only if a certain condition is met, otherwise the next instruction in the sequence is executed. So this corresponds to an if. A branch instruction in which the branch is always taken is an unconditional branch, so that might correspond to a go-to statement. And there are two common ways of generating the condition to be tested in a conditional branch operation. First, most machines provide a 1-bit or multiple-bit condition code. This code can be thought of as a short user visible register. As an example, an arithmetic operation AND could set a 2-bit condition code with one of the following 4 values: 0, positive, negative, or overflow. On a machine, there could be 4 different conditional branch instructions. Branch to location X if it's positive, branch to location X if it's negative, branch to location X if it's 0, and branch if it's location X to location X if an overflow occurs. In all these cases, the result referred to is the result of the most recent operation. Another form of transfer of control instruction is skip. The skip instruction includes an implied address. Typically, the skip implies that one instruction is to be skipped, thus the implied address equals the address of the next instruction plus one instruction length. You can skip more than one, but typically it's implied that you're skipping one. Because it does not require a destination address field, it is free to do other things. A typical example is the increment and skip if 0 instruction. And that one is abbreviated as ISZ. Procedure calls. These are self-contained programs that are incorporated within a larger program. You may recall this as functional decomposition, and this is one of the great ideas in computer science. And the book pictured here is Bierman's Great Ideas in Computer Science, A Gentle Introduction, and this is definitely worth a read. It's very high level and gives you an idea of what are some of the major ideas in CS. But functional decomposition or procedural abstraction is one of them. And basically this is making functions in your program. And at any point the program procedure can be invoked or called. The processor is instructed to go and execute the entire procedure and then return to the point from which the call took place. Two reasons for this. One, allows the same piece of code to be used many times. And two, it's modularity. And there are two different types of instructions that are special to these. One is a call that branches from the present location to the procedure, and a return instruction that returns from the procedure to the place from which it was called. So this is a couple things worth noting. A procedure can be called from more than one location. A procedure can appear within a procedure. This allows for the nesting of procedures to an arbitrary depth. So you could call one procedure, and then from that procedure you could call another procedure, or some languages even allow you to define a procedure within a procedure. Each procedure call is matched by a return in the call program. Because we'd like to be able to call a procedure from a variety of points, the processor must save the return address so the return address can so the return can take place appropriately and get back to where you called the procedure from. There are three common places for storing the return address. One is in a register, the other is at the start of the call procedure, or the third is at the top of the stack. Interestingly, a reentrant procedure is one in which it is possible to have several calls open to it at the same time. You are no doubt familiar with recursion, procedure that recalls itself. If parameters are passed via registers or memory for a reentrant procedure, some code needs to be responsible for saving the parameters so the registers or memory space are available for other procedure calls. A more general and powerful approach is to use the stack. When the processor executes a call, it places the return address on the stack. When it executes a return, it uses the address on top of the stack. In addition to providing a return address, it's also necessary to pass parameters a lot of the times. These can be passed in registers. Another possibility is to store the parameters in memory just after the call instruction. In this case, the return must be to the location following the parameters. Again, both of these approaches have their drawbacks. If registers are used, the call program and the calling program must be written to assure these registers are used properly. The storing of parameters in memory makes it difficult to exchange a variable number of parameters. Both approaches prevent the reuse of reentrant procedures, which is kind of a bad thing. So, Intel X86 and ARM operation types, and this is a pretty detailed section of the book, so we'll just cover it pretty briefly. The X86 provides a complex array of operation types that include a number of specialized instructions. The intent of this was to provide tools for the compiler writer to produce optimized machine language translation of high-level programs. 4 instructions to support procedure call return, call, enter, leave, and return. And there's a discussion in the text as to, why enter was introduced, but why it's not the optimal solution. When a new procedure is called, the following must be performed upon entry to the new procedure. Push the return point on the stack, push the current frame pointer onto the stack, copy the stack pointer as the new value of the frame pointer, and adjust the stack pointer to allocated frame. In 1996, Intel introduced MMX technology into its Pentium product line. The MMX is a set of highly optimized instructions for multimedia tasks, video and audio data. They're typically composed of large arrays of small data types, and 3 new data types were defined in MMX: packed byte, packed word, and packed double word. Each data type was 64 bits in length and consists of multiple smaller data fields, each of which holds a fixed point integer. ARM operation types: load and store instructions, branch instructions, data processing instructions, multiply instructions, parallel addition and subtraction operations. For those, in addition to the normal data processing and multiply instructions, are a set of parallel addition and subtraction instructions in which portions of 2 operands are operated on in parallel. For example, add 16 adds the top half words of 2 registers to form the top half word of the result, and adds the bottom half words of the same 2 registers to form the bottom half word result. These instructions are useful if in image processing applications and similar to the X86 MMX instructions. Extend instructions: several instructions for unpacking data by sign or 0 extending bytes to half words or words, and half words to words. Status register access instructions, and this is where ARM provides the ability to read and also to write portions to the right portions of the same register, of the status register. Sorry about that. You can see a lot more about those in section 12.5, and I think that just about finishes it up.